Okay, let's get back into things. So, any questions about the proofs that we have done to show all these problems being undecidable? Okay, so you may think, I hope you think this, that these proofs where we're building a machine where it has this property if M accepts W, and it has this other property if it doesn't, meaning that it's in the language that we're looking at in one case and it's not in the language in the other case. You may think, okay, well, could we try to generalize this to any other problem that we want to consider? So maybe we can think of determining whether a Turing machine's language is all strings, for example. Instead of just all empty, whether the language really is empty, we can test whether it's sigma star or something. And you can probably guess that isn't decidable either. We can test whether the language is a context-free language. So maybe we can't go all the way down to a DFA, but maybe we can just go to a context-free language instead. That's undecidable too. What if we want to check whether the machine's language is infinite or not? So any infinite language. Well, that turns out to be undecidable too. So in all of those cases, you can come up with a Turing machine that has the language that we want. So in the last case, we can make a machine that does have infinite language, and we can make another one that has finite language. And so what we would do is we would make the machine, so like in step one in all of these proofs, we make the machine that has the behavior of one if M accepts W, and the behavior of the other one if it doesn't. So that's the essential idea. So I hope you're hungry. So we're going to prove something called Rice's theorem. One of the other times I taught this class, I wanted students to use Rice's theorem in a homework. So what I did is I said, hint basmati. Because rice is related to rice. Computer science humor. All right. Yeah. So let's prove something called Rice's theorem. So what is the idea here? So let's talk about something called properties of Turing machine languages. So the ETM one and the regular TM one and the ones that I just mentioned are all properties of Turing machine languages. So what do I mean by that? So, and also, what do I mean by property? So property, all that is a set of Turing machine descriptions. I'll say encodings, because that's the terminology we did. So ETM is just a bunch of Turing machine encodings. Regular TM is just a Turing machine encodings. What about EQTM, where it has two machines? Is that the same thing? No, because it's two Turing machines in the encoding. So here it's single machine encodings. If we wanted to check whether a single machine has an infinite language or not, that's a property too, because it's just a set of Turing machine encodings. Okay? So what do I mean by a property of Turing machine languages? So what I want this to indicate is the only way to differentiate whether you're in the property, the set of the encodings or not, is entirely on the Turing machine's language. So the only thing that matters is the language of the machine. So let's go back here. So suppose that instead of talking about regular TM, which is just entirely on whether the language of the machine is regular or it isn't, I said the language of the machine is regular and has at least 7 states. Is that a property of the language itself? Or could you have a machine that is regular and another one that is regular, but one of them is in regular TM and the other one isn't. If I said, and at least 7 states. Yeah, because I can make a machine that has fewer than 7 states that has a regular language, and another one that has at least 7 states and also has a regular language too. So, but one of them is in the language and one of them isn't. We could talk about that problem if we wanted to, but we want to talk about a certain type of problem called property of Turing machine languages. So the only criterion that I want to exist is the only thing that matters is the language of the machine itself. We're not talking about the number of states it has or anything else, just the language itself. Okay, and so what do I mean by this? So here we say if M1 and M2 are arbitrary Turing machines and they have the same language, then either both have the property or neither do. Okay? So by have the property, I mean is they're both in the language that we're considering. So the property of Turing machine languages. So the only thing that matters here is if they have the same language, then they are either both in the language we're talking about, so think regular TM or ETM. Either they're both in that language or they're both not. Could it be the case that we have 2 Turing machines with the same language, where one of them is in ETM and the other one is not in ETM? No, because if they are both in ETM, then if they have the same language, then they're either both empty or they're both not empty. Does that make a lick of sense? Anyone completely lost? Anyone semi-lost? Okay, anything I can try to clarify? Anything that's not 100% clear?
Can you just say it again?
Yeah. Anyone know Scott Myers of C++ fame? So he's a famous C++ programmer, retired a few years ago, and he said in one of his talks, he was talking about something called R-value references. If anyone knows what R-value references, good for you. And he was giving a talk at a conference, and he said a technical statement, and then he said, if you repeat it to yourself 100 more times, you're almost halfway there. So it's the same idea here. If you repeat it to yourself over and over, you are closer. So what do I mean here? The only thing that should matter of what for these types of properties, not an arbitrary language in general, just these ones, the only thing that matters is if they have the same language, then they're either both have the property or both don't have the property. So think of regular TM. Could I have 2 machines that have the same language where one of them is regular and the other one isn't? No, because they're the same language. If I augmented this to say and has at least 7 states, that depends on something else other than the language. And so I could have them both be regular, one having at least 7 states and one having fewer. And so one is in regular TM and the other one isn't. If we talk about ETM, I guess I don't have the definition here. If they have the same language, then they're either both empty or both not empty. Okay, does that make sense? So these are the types of things I'm talking about. Properties of Turing machine languages. The only thing that matters is the language. Okay. But let's suppose I asked you to solve this problem or show it's undecidable or whatever. I want all Turing machines that have a language at all. Is there any Turing machine that doesn't have any language at all? No, there doesn't exist one. Every single Turing machine has a language. So in that type of problem, what is the answer always? No matter what machine you get, what should you always say? Yes, you should say except, because every Turing machine has a language. And so therefore, no matter what I get, I should say except. So that problem is decidable. Well, what if I wanted to say the language which has no Turing machines in it? If I get an arbitrary Turing machine, what should I say? I should say reject, because it's not in there.
What do you mean by the language which has no Turing?
Yeah, so what if I talked about, let's see. Okay, so this will seem like a stupid language, but it's just to illustrate the point. What if I talked about this language of Turing machines? So M is a Turing machine. So there's no need to write this down because this doesn't really mean anything. And M has two languages. Does any machine have that property? Have two different languages? No. Every machine has exactly one language. So therefore, there's no Turing machine in this because no machine has this property. And so therefore, no matter what machine we get, we just say no, it's not there. So this problem is decidable too. So we need to talk about, instead of just arbitrary properties, we need to talk about what are called non-trivial properties. So what does non-trivial properties mean? So non-trivial is not one of those two weird cases I just mentioned. So by non-trivial, we mean there's some machine that does have the property, and there's some machine that doesn't. And that's it. So what does non-trivial mean? Some Turing machine has the property, and and some other TM does not. Okay? Cool. So this is actually all we need. So what does Rice's theorem say? So Rice's theorem, although Emil Rice didn't actually say this like this, but this is basically the same thing as what he said, but just in a different context. So what he said, although he didn't say it, is that every non-trivial property of Turing machine languages is undecidable. Every single one. So instead of just going, okay, we proved this is undecidable, then we proved this, then we proved this, then we proved this, this will immediately tell us that every single one of them is undecidable. That's kind of shocking. So anything that is non-trivial, really, about a Turing machine, you can't solve. Isn't that weird? So how would you actually prove this? So it's late. I know you guys don't want to see a very complicated, detailed proof right about now. And I don't really want to do it either. So the good thing is I'm going to resort to the Sipser book because the proof is in the Sipser book. If you go to, it's in the back of chapter 5, I think. It should be one of the solved exercises like 5.30, 5.31 or something. And the proof of actually how that's done is in the back of the book. But I'm just going to sketch it right here. So I'm just going to purely sketch it. I'm not going to do all of the proof here. So we're going to let P be a non-trivial property. Of Turing machine languages. Should fix that Y. So let's refresh ourselves. What does non-trivial mean? Right. So some machine has the property, some machine doesn't. And so the method of how we would actually prove such a thing is we're going to try to solve ATM while building a machine that behaves like one machine that has the property, and the other case being a machine that doesn't have the property. Well, we don't know what this property actually is. What machines have it and what machines don't. I know there's one machine that does and one machine that doesn't, for sure, because that's what it means to be non-trivial. So what you actually do here is you pick a machine that has the empty language. So let M1 be a TM that has empty language. Well, we don't know right here whether it has this property P or not. It might not. So what we can do without loss of generality is we can say that, that it doesn't have the property. So without loss of generality, assume M1 does not have property P. And let T be any Turing machine having property P. So there are some details here that I'm skipping, purely just for our own sanity. Because it really is it warps your mind, this proof, a little bit. But it's actually pretty interesting because it's almost the same proof as the ones that we're doing before, just generalized. That's all it really is, which is pretty nice. So what you do here, so I'm just going to sketch the idea. So then we build a supposed decider for ATM by making a Turing machine that behaves like M1 always. So it always behaves like M1 unless M accepts W, which is the qualification for ATM, in which case it behaves like T. So by default, it will behave like one machine that doesn't have the property, and which has empty language, which is convenient for us in this case. And then if M accepts W, then I'll accept the strings that are in T, that the Turing machine T accepts. So we behave like T, which does have property P. So don't read too much into this, because this is really the entire proof, minus details. So don't read too much into this because you're not going to actually prove things via this way. You're going to prove things undecidable by resorting to Rice's theorem. So what you do is you're presented a non-trivial property of Turing machine languages. You show that it's a non-trivial property, and then you say, by Rice's theorem, this is undecidable, which is a lot easier. Yeah.
So when you say that we prove that it's a non-trivial property, does that mean that we need to prove it? I mean, I'm assuming you're going to make an example.
Yeah. I'll do examples. And this is like the one concept in this class that is far better to see an example than to just do a proof like this and just say, yeah, you can do this in general. It's much better to do an example because you'll all breathe a sigh of relief when you see how simple these proofs are. Yeah.
What means the W log?
Yeah, so the W log here means without loss of generality. So this means that I can assume this without changing the validity of the proof. I can assume that that is true. And the reason why I can assume that is that purely because decidable languages are closed under complement. And so I'm trying to show that P is undecidable because that's what Rice's theorem says. And so if it's undecidable, then if I flip the roles of P and its complement, then P complement is also undecidable, and then I can just change the roles, and then I get without loss of generality right there. Because if M1 does have property P, then I just flip the roles, and then I'm all set. Cool. Other questions? Okay, so let's actually prove the other languages that we've done before using this framework. So let's do ETM again, which we know to be undecidable, but let's actually prove it via Rice's theorem this time. So this is the problem we talked about before. Can I apply Rice's theorem to every possible problem with Turing machines? Could I apply it to EQTM, the equivalence problem? No, because that has two machines in it. I can't apply it to ATM because it has a machine and an input with it. But if it's just a single machine with the only thing related to it being the language, nothing about like the number of states or anything, then I can apply Rice's theorem. So let's try to apply Rice's theorem here. So we'll do a proof here by Rice's theorem. So in order to apply Rice's theorem, what do we actually need here? So we need to show what about this language ETM. Yeah, it's not only a property of Turing machine languages, so the only thing that matters is the language of the machine itself, but also we need to show that it's non-trivial. And if we show both, then by Rice's theorem, we're okay. So let's do the property of Turing machine languages first. So let's see. How do I show that this is a property of Turing machine languages?
We find an example of a Turing machine that has a language 0, like empty.
That's the non-trivial one. So what does property of Turing machine languages mean? It means if I have two arbitrary machines, so any two machines at all that have the same language, could it be the case that one of them is in ETM and the other one is not in ETM? So in other words, if I have two arbitrary machines with the same language where one of them is empty and the other one is not empty, could that be possible? No, it should be more emphatic than this. If they have the same language, could one of the languages be empty and the other one not be? If they're the same? No, good. Okay, so how would you actually write this? So you would say if M1, M2 are arbitrary TMs with the same language, so L of M1 is equal to L of M2. Then either both are empty or both are non-empty. And that's it. Yeah.
To me, it seems like you use the definition of a property of the language and change the specific language here.
Mm-hmm.
That's how we prove it?
Yeah. Isn't this a lot easier? So what was the other thing that we needed to show? Show it's non-trivial. Cool. So how do I show it's a non-trivial property? So how do I show ETM is non-trivial? Yeah, so I find one machine that has empty language, and I find another machine that doesn't have empty language. Can I make a Turing machine that has empty language? Yeah, that's easy. So M1, here I'll just say let M1 be a Turing machine with the language of M1 being empty, and let's let M2 be a Turing machine with L of M2 being sigma star, for example. And that's it. So didn't we just show that it's a non-trivial property of Turing machine languages? Because we gave a machine that does have the property and one of them that doesn't. And we showed this property of Turing machine languages, which means that the only thing that matters is the language. Yeah?
You don't have to define the Turing machine itself?
No. Unless it's sufficiently complicated, then there's no reason to. Yeah. So like for these ones, it's pretty easy to do. In fact, we can even do it ourselves right here. You can just say, the first one, I have QReject as the start state, and QAccept being over here, not connected to anything. And then we can define transition. Actually, we don't need transitions in this case. And in the other case, we would have QAccept as the start state and QReject as the other state. But you don't even need to do that here. It's not worth your time to actually do that sort of thing. As long as it's not incredibly difficult language to work with, then yeah, so like these ones are sufficiently easy to work with. Oh, so by these two, what do we know then?
That is undecidable.
It's undecidable by what? By Rice's theorem. So the most important three words right here, by Rice's theorem, ETM is undecidable. Who thinks that's far easier than doing it the other way? Yeah, so if you can apply Rice's theorem, should you do it the other way? No, this is far easier. If you can apply Rice's theorem, do it. Okay? So I want you to not have to suffer through these. If you can apply Rice's theorem, then do it. If you can't, well, you can't. But will the other method work in the general case? Not just for these ones. Not just for properties. Yeah, it'll work in the general case. But in a lot of cases where you just have a single machine, often you can apply Rice's theorem directly, and it's just far easier. Any questions about that? Yeah.
Why did we say that? L of M1 equals to L of M2?
Yeah, because we wanted to show that there's one machine that is in ETM, and there's another machine that isn't. So in the case of M1, it's a machine that has empty language, so it's in ETM, and M2 is a machine that doesn't have empty language, so it's not in ETM.
I'll ask you.
Okay. Other questions about that? Cool. Let's do one more, and let's do a different example than what we've seen before. Let's see, what would be interesting? Let's do the finite one. So I'm going to call it finite TM. So this is just a bunch of machines where M is a Turing machine as before, and the language of the machine is finite. So it only has finitely many strings in its language. So do you think that this qualifies to fit under Rice's theorem, just by looking at it? Yeah, it's a bunch of single machine descriptions. The only condition on here is that the something about the language. So it seems like we can apply Rice's theorem, and we can. So let's try. So let's try to do proof by Rice's theorem again. So again, what do we need to show in order to apply Rice's theorem?
Property of the Turing machine language.
So we need to show its property of Turing machine languages and it's non-trivial. Cool. So property of TM languages. So what does that mean? It means that if M1 and M2 are arbitrary Turing machines, and they have the same language, could it be the case that if they have the same language, one of them is finite and the other one isn't? No. So yeah, so that's what we have here. So either both are finite or both are infinite because they have the same language. If they have different languages, we don't care. As long as they have the same language, that's the only thing that matters. So there's no other differentiator other than the language itself. Yeah.
So for the section with property of TM languages, is it pretty much always of like the same format where you
Yeah.
say if they're arbitrary?
Yeah. I'm going to say again, isn't this a lot easier? Yeah. So it's pretty much just it's pretty much algorithmic to write out the proofs like this because it's if M1, M2 are arbitrary Turing machines and blah 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 blah, either both are the property name or both are not the property name. You can do a string substitution from the language description. Anyway. You can't apply it to every language like this. So if I made other qualifications in the language description, then it may not work. It's just because the only thing that matters is the language, then we can apply it. Okay? Okay, so then we want to show it's non-trivial. Trivial, yep. So can we find a Turing machine that has finite language and another one that doesn't have finite? Wait, couldn't we just use the same two examples as before? Yeah, one of them is finite, the other one isn't. Interesting. Nope. Zoop. Copy. Paste. Oops, I got some more with it. Ah, done. Who's liking Rice's theorem now? Isn't Rice awesome? Yeah.
Can you? I just can't think of an example of a property that we can't do this. Can you give an example of a property that won't work?
So are you talking about the property part or the non-trivial part?
Actually, the beginning, like the definition. I'm trying to find an example of something that we cannot apply that. Like before we were saying that the language has to be empty. Now that is finite.
Yeah, so I'm going to do it in red. So let's make another qualification, and M has 7 states. If I can write 7 states. So now if we have 2 machines with the same language, then there's this other qualification that one of them could still be in the language and the other one isn't, even though they have the same language. Because one of them could have more than 7, can have 7 states and the other one doesn't. So if we strike out that condition, then the only thing that matters is the language.
Is there any case where one of those details that we have to actually think about and not just do the template thing? Do we have to prove that, or we can just maybe write some analysis like that? Where
you would have to prove it in that case. Yeah. So the way that you would do it is, I haven't introduced the notation yet, but the way that you would do it is you would make the ATM machine, and then you would do the same style of proof that we did for the other examples. Then what you would do is you would just say, keep adding states until you have the right number. So if you have, let's just say I said, and M has at least 7 states. Then what you would do is you would say, keep adding states, just dead states, to the machine until you have at least 7. And
that makes a difference.
yeah, and so therefore, no matter what happens, the 7-state condition is always satisfied. And so what you would do, so this is not Rice's theorem. And then the only thing that would matter whether or not it's in the language is the language of the machine. And then that's what the decider will tell you. So yeah, so I won't pull some kind of trick like that. I'll most likely do something like these Rice theorem examples because it's far easier. But I encourage you to look at the actual proof of how it actually works because it's basically what we've done before, just in a generalized form. Okay, so then what can we conclude based off of these two parts? Yeah, so finite is undecidable. So by Rice's theorem, what did we call it? Finite TM is undecidable. Sweet. So yeah, it really is not that hard to actually do these proofs. The hardest part, in my opinion, is the non-trivial part, because it's non-trivial. What you would do there, because you have to think about, can you make a machine that doesn't have the property and one that does? So as long as you can make one machine that has the property and one that doesn't, as long as you can think of a language that in this case is finite and one of them that's infinite, then you're all set. In this case, empty set and sigma star work. You can pick any finite and any infinite language. It doesn't matter. It's just that these two are easy to work with. Okay, any questions about these? Cool. So let's go on to the next topic, at least for a little bit. So it's kind of sucky that these Turing machines, basically anything that you care about them are undecidable. So anything that you want to ask at all, there's no way to do it. There's no algorithm at all to do it. And you think, okay, Brian, my computer has a finite amount of memory, fixed amount of memory, right? So let's just suppose that I'm not accessing some storage anywhere else. I'm fixed to the computer that I got. And I could add memory to it if I wanted to, but the problem is at some point there's going to be some maximum for which I can't add any more memory. So, but here's the thing. So then you think, okay, wait, so you have a fixed amount of storage, so that must mean that you have a finite number of combinations of memory contents in your computer. So wait, isn't that a DFA at that point? Because there's only a finite number of combinations and you can't have any more. So we know that we can solve problems on computers in principle that are not regular, right? We can solve 0 to the n, 1 to the n on a computer. What's the issue? The issue is, what if I try to make a string that's extremely long? That's like, the string itself is bigger than the memory amount of my computer. So what would I do in that case? So the way that we're going to do it here is, think of a Turing machine. On a Turing machine, there's always room to store the input. So let's try to think about a Turing machine model where instead of allowing you to have as much tape as you want, let's just store the input itself. Just entirely the input, and you can't access any other memory. It's just the input itself. But you can write on the contents of the input as you want, just like a Turing machine does. But you can't like keep going to the right and keep accessing more memory. Because one of the issues with like trying to decide ATM was, well, we could try doing this. So if we have some configuration, so contents of the tape, and at some point later, if we have the exact same contents of the tape, where the tape has in exactly the same position and we're in the same state, aren't we going to do the exact same thing again? Yeah, because a Turing machine is deterministic. If we're in the exact same situation again, we're going to repeat ourselves. Okay? So just like in your computer, if you have in your program space, if you have the exact same memory contents and you're not accessing anything else outside, you're going to do the exact same over again, exact same thing over. So let's try to restrict the Turing machine model in a way that makes sense to try to avoid that issue. So instead of having to store as much memory as we want, let's just restrict it to what the input actually is. So that's the next model of computation we'll talk about. It's just a restriction on what Turing machines can do. So these things are called linear bounded automaton. So it's called an LBA. Is a Turing machine that has its tape being exactly the length of the input plus 2 delimiters. So what do I mean by that? I mean that, so instead of having an infinite tape, it's a fixed length tape for each input. So if I put a bigger input on this LBA, the tape is going to be bigger. It's just enough to store the input itself. There's no infinite blanks to the right business. So what we have here is that we're going to have a delimiter on the front and a delimiter on the end to help, and we'll see why we need those. And then in the spaces in the middle is where the input actually is. So if we have n characters, then the tape has n plus 2 cells. So the middle n are for the input, and then the one on the front and the end are for the delimiter. So the reason why we have these delimiters here is there's no reason to ever shift the input. So we would want an easy way of figuring out where's the beginning of the input and where's the end. Well, if we wanted the beginning, an idea for Turing machines was just to shift the input and put a special symbol on the front. We can't do that here. So we're going to allocate for you the delimiter on the front. And if we wanted to know the last character, what we would normally do is go to when we hit the blanks and then move back 1 character. But we don't have that here because there are no blanks. So we would have a special delimiter on the end. Okay, great. So don't read too much into this other than the tape is fixed and you can't allocate anymore. So if you go to the delimiter on the end, you have to go backwards. Okay? And if you hit the delimiter on the front, you have to go forwards. So there's no like jumping off the end of the tape or keep going to the right business. You must stay within the contents of the tape itself. Okay. So let's talk about the problems that we've been talking about with Turing machines, DFAs, and whatnot. But now let's talk about LBAs. So the first one we talked about before with Turing machines and whatnot is the acceptance problem. Oops. Shoot. I went on autopilot there. So it's machine and input. So M is an LBA, not a Turing machine here. And M accepts W. So the behavior of the LBA is identical to a Turing machine, except now we can't keep going as far as we want to the right. We can only go to where the input is plus 1 character for the delimiter. Okay. So, is this problem decidable or undecidable? Who wants to flip a coin? What do you think? It's decidable. Isn't that cool? That just by restricting it just to where the input is, and in fact, if we, ignoring just LBAs, if we just restrict the input to like maybe the input plus some other characters, and we just restrict it to there if we needed additional space, it's still gonna be decidable. As long as we restrict the tape, then it remains decidable. Yeah.
Is it the same concept in regular languages that, or like every finite language is regular? Or is every finite tape length is?
The problem, so a good question. So the problem here is that we're writing over the input and we can go backwards. So it's not like, okay, it's just a DFA and it moves forward. If it really did just move forward, then the language is regular anyway. So the problem is here that we can move back and we can change the tape contents. So yeah, go ahead.
So could the language never be like infinity because it has a delimiter?
So good question. So by this you mean the machine runs forever. Yeah. So could an LBA run forever? Yeah. So what it can do is, okay, look at the first character, move right, then next transition, move left, move right, move left, move right, move left. It could do that if it wanted to. It's just a Turing machine. But in this case, we can't like keep going to the right, but we can still have the same behavior as a Turing machine. So it can keep going left and right and do this infinite behavior. So it's not the case that LBAs can't run forever. It's can we determine that they have run forever? Well, let's see. Well, here's the thing. If we have fixed the input, there's only a finite number of combinations of tape contents. So let's actually prove that this is decidable. Well, let's say there are, there are G, I'm trying to remember the notation from the Sipser book. Let's say that there are G different tape symbols. Other than that, let's say that there are Q different states. And the input length is N. Okay? Well, let's see. How many, and let's just say for ease of use, we can't change the delimiters, for example, just to make the argument easier. In general, you could, but let's just make this easier. So the only things that we can change are the N cells that were given, where the input actually is. So how many possible tape contents then of those N cells? Well, how many possibilities do I have for the first one? I have G. What about the second one? A G. If I have N of them, how many do I have in total? G to the N power. So by this, there are G to the N different tape contents. But maybe we visit all of those different tape contents, and then after all that's done, we're now in a different state. That could be possible. But how many states are there? There are a Q of them. But maybe we do all those possibilities, and then now the tape head moves one position. How many possibilities, ignore the delimiters, how many possibilities are there for the tape head position? N. Wait, what is a configuration? A configuration is tape contents with the tape head location and what state we're in. So how many possible configurations are there? Well, we can be in any one of the tape contents, as well as any of the states, as well as any location. Well, isn't that just g to the n, the number of tape contents, times the number of different states we could possibly be in, times any possible one of the cells that we could be in. Those are the number of possible configurations there are. We may not visit all of them, but that's the total number of possibilities. Wait a second. So those are the total number of possibilities. What if we run this machine for that number of steps plus 1? What has to happen? There must be some repetition somewhere. So if there's a repetition somewhere, is this LBA going to do the exact same thing again? Maybe a repetition occurred earlier, but now we guaranteed one occurs. So that's the essential idea. So to decide A sub LBA, so on input M, where M is an LBA. Oops, sorry. I went on our autopilot again. MW, where M is an LBA and W a string. What we would do is run M on W for G to the N times Q times N plus 1 transitions. I should actually amend this to say for at most that number, because maybe we reach the accept or reject state before that occurs. So I'm just going to say at most here. Yeah.
You mentioned, right before you started writing this, you mentioned that if we do the number of configurations plus 1, we guarantee a repetition. But then you said that maybe a repetition happened before?
Yeah, that's totally possible. But if a repetition occurred before, it doesn't really matter as long as I can determine in a finite amount of time whether or not a repetition occurred.
Okay.
So if it may take me longer, that's okay too. It's just here I'm guaranteeing it for all cases. For like a specific machine, we could actually make a determination faster, but it's just, we got to do it in general. Okay, so if M accepts W at some point along the way, so if M accepts W at some point, then we accept. Otherwise, if M has not halted by now, then it never will, meaning that we should reject. And if it rejected halfway through, we reject as you might expect. So all we're really doing here is we know the number of possible things that could occur during the simulation at most. And so if we do one more, we must have done repetition somewhere. And so that's it. So we can actually decide A sub LBA. Isn't that kind of cool? Okay, any questions on that? So now we could possibly get into a philosophical issue about whether the programs that we are really running are really LBAs or are they really Turing machines. So we can get into that. Do I have time to introduce? So I'll introduce this. We'll talk about it next time. Think about this language. What about the emptiness problem for LBAs? So if M is an LBA and the language of M is empty, we can't apply Rice's theorem here because it's not a property of Turing machine languages. It's LBA languages. And there's no, as far as I know, Rice's theorem for LBAs. So is this one actually decidable? So I don't want to get into clickbait or anything, but the answer will surprise you. And I'll talk about it next week.